an hour or a smidge over would be great, and that would give us a couple of minutes to finish. But you don't need to pull it out. I mean, if we leave end a little early, we'll end a little early. So take it away whenever you're ready, Toby.
Great. Yeah, I may not take a whole hour. We'll see. Okay, cool. Let me start my timer. Yep. So it's great to follow Jeff, really, because he's talked a lot about these kinds of bidirectional systems and learners and lenses. And really, a lot of this stuff is going to come up in what I'm going to say, which is kind of another kind of perspective, appropriately for a workshop on category theory, for what it means for systems to do learning. And in particular, it's a kind of perspective which comes from a more statistical point of view, rather than this kind of differential point of view that Jeff was talking about earlier. Now, I'm sure that in some kind of abstract sense, say if we think information geometrically, the two stories are probably very similar, even in the mathematics, but at least in terms of how people use them, they're a little bit different. Okay. If I can change my slide. Okay. I don't know, there's a little bit of delay in my slide changing for some reason. Right. So my background, as I mentioned earlier, is really in sort of computational neuroscience and philosophy and things like that. And I'm kind of interested in questions like, how do brains learn the structure of their environment, or how or what even do neural circuits compute, and what's the kind of right notion of computation for neural systems? And how does the world inside my head relate to the one that's kind of out there that we all participate in? And how should we make sense, as I mentioned earlier, how should we make sense of this kind of fragmented and underspecified literature that we get in neuroscience and psychology? And I came across this framework that I'm sure some of you have heard of called the free energy framework. And it seemed to me seemingly the closest we've come to something like a unified theory of intelligent systems. And interestingly, it seems to have some kind of neural grounding, in the sense that although some of it is quite abstract and specified in terms of kind of abstract statistical problems and algorithms, there's some literature which attempts to translate those algorithms into dynamical systems, which look a bit like models of neural circuits do. The trouble with this literature is that it's kind of mathematically quite confusing, and it's kind of unclear. And even though it has clear signs of compositionality, and I thought to myself when I was struggling with these questions, that one thing that might be productive to do, particularly because it seemed to relate to some of the things that were going on in this kind of cybernetics world, for things like the lens kinds of things that Jeff was talking about to do with machine learning or economic games, it seemed to be productive to have a stab at, formalizing this free energy framework, this kind of thing called active inference. And so in this talk, I'm going to kind of frame the background to it, the kind of categorical mathematics for doing probability and statistics in what are known as Markov category. I'm going to talk about Bayes' rule a bit abstractly. It's going to turn out that it has a kind of bidirectional structure, very much of the kind that we see in Jeff's learners. And indeed, there's a kind of functoriality property that crops up there too. So we get a thing called Bayesian lenses, which are things that kind of do prediction. Something like Jeff's systems, which act and try to update. These are things which kind of predict and try to improve their predictions. Somebody asked afterwards about how do we know that the kind of systems are doing well at learning. And so I've got a construction of a thing called a statistical game, which is like a lens with some loss function that measures how well a system is doing. And the thing that predictive processing models do, at least in this free energy literature, is that they translate things like statistical games into dynamical systems. So I'm going to talk a little bit about open dynamical systems, so dynamical systems which we can somehow compose. And this will give rise to something that I call an approximate inference doctrine, which is a kind of functor, what we might call a dynamical semantics for inference problems. Okay, so there are kind of two basic ideas driving this kind of work. One is this notion of active inference. And so first of all, I should say what I mean by that. It's really very simple. If you're an embodied, adaptive, or intelligent system, you can sort of do two things. You want to survive, and so one thing you can say, and you have some perspective on what the world is like, a model of the world inside your head. And so one of the things you can do is you can improve your model of the world. And so the way this works in the kind of statistical literature is that we say that we can do prediction. So we predict the world, and then on the basis of our prediction, we can somehow update our beliefs. So this kind of might go backwards like this, or we can instead try to change the world to make it more lined up with our beliefs. And so this is kind of something like action. And the thing called active inference is a set of ideas that says, both prediction and action can be framed in terms of something a bit like Bayesian inference. And as I mentioned at the start, the other motivation I have is in neuroscience, the question of how do neural circuits solve hierarchical inference problems. So that means you might know if you in visual cortex, you have this kind of hierarchy of abstraction of representations that are increasingly object-like, or as you get further away from low-level visual cortex, where they're very kind of simple visual representations. And there are people who've done work trying to relate these two things. So they kind of do things which look a bit like turning some kind of abstract statistical problem into a dynamical system. And so there is work from Carl Frist and colleagues, I've got a citation here, which kind of does something like that, but it's not very kind of clearly or compositionally expressed. But before we can get there, I want to talk a little bit about categorical probability theory. So how should we think about statistical problems using the language of category theory? And so to start with, we need a notion of probability distribution. I'm going to talk, because it makes life a little bit easier, only about what are sometimes confusingly called categorical distributions or discrete distributions, or slightly more generally, distributions which are finitely supported. So really, they're just functions from a set into the unit interval. So a distribution over this set X is going to be a function from X into this unit interval, and it says for each point of X, what's the probability of that point under the distribution. And this mapping of sets to distributions on those sets gives us a functor, which I'm going to write as D. Its action on morphisms is important, although not particularly crucial for the talk right now. But I should say what it does is it does what's known as the push forward of probability distributions. It says if I've got to map a function from X to Y and a distribution on X, I can somehow push this distribution pi. I write pi because it sounds a bit like prior. I can push, and it's a bit like P. I can push this distribution pi forwards along F to get a distribution on Y. And so how does this work? Well, okay, so pi takes points in X and gives me numbers between 0 and 1. And I need a function which goes from Y to numbers between 0 and 1. And the way this works is, given a point of Y, I just sum over all of the points in X which land at Y using F. I sum their probabilities up, and that gives me a probability because, of course, pi is a probability distribution, so it's normalized. I possibly should have said that axiom here, but I'm going to assume that these things are probability distributions. Now, this functor D is also what's known as a monad. Britt mentioned this term monad right at the beginning. We don't need to say precisely what this is, but it means it has something called a multiplication. It's like a monoid, as we saw earlier. Monad is a kind of monoid. It has a multiplication which kind of does convex combinations of distributions. So if I've got a distribution over distributions, I can sort of average over them to just get a distribution. And I've got this thing called a unit, which says given a point in X, I can get a distribution over X, which is just this thing that's sometimes called the Dirac or point distribution on that point. And that's just the thing that gives me a probability of 1 only at that point. So this thing, it collects into a functor, it collects into a monad. It's called the distribution monad or functor. And it's going to be important in the sort of background setting for this categorical probability language. I'm going to want to talk a little bit more abstractly about things called Markov categories. Now, I'm going to construct a particular kind of Markov category using this distribution monad. And we could think of the objects of this Markov category, they're just going to be sets, but we could think of them more abstractly as something like spaces. And the morphisms of a Markov category are going to be something like conditional probability distributions, or slightly more abstractly, something that we might call stochastic channels. Now, you sometimes see as conditional probability is written like P of y given x. And the thing is, if we say, okay, this is a function, if we think this depends on x, then really this says, given a point in x, I get a distribution over y. And I think because this notation P is always so overloaded, and if you see P of something written down, you don't really know what distribution it's referring to. I always write a little subscript to say, where does this distribution come from? So a morphism in this category, KLD, I write KL for Kleisli, because of the, for historical reasons, really, is going to be a function from, so if it's a morphism x to y, it's really a function from x into distributions on y. It's this kind of conditional probability intuition that I just mentioned. So it says, for each point x, I get this distribution PC, P sub c on y. I've said before that there's this kind of special object in these things called monodal categories. This is going to be a monodal category in the sense that we'll be able to put things in sort of parallel. This is how we get joint distributions, as we'll see in a moment. And these things are things that we call states, if they're channels from this monodal unit into a space. In the category of Kleisli category of the monad, it's really a map from the set with one point, that's just a singleton set, into x, into distribution, sorry, on x. And this just picks out a distribution. So really these states, the things that I drew with a triangle before, are just probability distributions. So they're conditional probability distributions with no conditionality. Okay, and suppose we've got like two of these stochastic channels, two of these probability distributions, one like we'll C from X to Y and one from Y to Z, then we should be able to compose them. And how does this work? Well, this works by somehow kind of averaging over the points in Y. So C is going to say, given a point in X, I get a distribution in Y. And D says, given a point in Y, I'm going to get a distribution in Z. Well, I use the kind of functoriality of D to promote this into a map DD from DY to DDZ. And this says, okay, so now given a distribution Y, I get a distribution over distributions in Z. But hold on a minute, I have this kind of monad structure, which allows me to reduce distributions on distributions just to distributions on the original space. Okay, that all sounds very complicated, but it's actually just this intuition that I mentioned. It's just saying, okay, if I take my point in X, I need now a distribution over Z. Well, how does this work? I've got this conditional probability distribution, P sub C of Y given X, and this other one, P sub D of whatever given Y. Well, I can just sort of multiply these things together for all points in Y and sum them up. And this just gives me a distribution over Z. It's really just marginalizing over this intermediate space. And so this thing gives me a category. The identities are these if I've got X to X as a stochastic channel, that's X to D, X. It's really the thing that takes a point and gives me the delta distribution on it. So it's the same, or the thing I wrote is the monad unit eta before. Okay, so that's a bit of a sort of whirlwind introduction to categorical probability theory. We also, because as I say, it's a kind of it's a monodal category, I'm going to start drawing these things with pictures. The kind of monoidal structure allows us to write down like joint states. So if I have this omega on X and Y, I'm going to draw X wire and Y wire. Really, this is just a distribution on X and Y. So it takes in a Y, an X and a Y and gives me probability. And often I could factorize things into this form that is sometimes called a generative model. So that's just like a prior, this pi is like a prior, and this C bit is like a likelihood. And it says that the probability under the joint model is just the probability of the, of the prior here times the conditional probability. This is a kind of standard law of probability theory. So I can sort of factorize things like this. And if I have such a joint state or joint distribution, I can sort of throw away, using this discarding structure that I indicated before, one of the wires, discard it, and this just gives me the marginals on the other wire. So if I throw away the y, it says, oh, just average out all of the y's. And this is going to give me the x marginal, which is just pi. You see this by kind of just saying, okay, well, I throw away c, I've got nothing there, and now I've just got this simple thing here. Similarly, on the other side, I can throw away the x wire, discard that. And really, that's just saying, oh, all right, this should be a discard here. This says, okay, I throw away that wire. Oh, and now I've just got a kind of trivial thing, nothing copied here. And so I get this thing, which is the composite. Okay, and so what's the composite? Well, it's just the other marginal. It's this thing which is the composite channel, composite conditional probability distribution. It's just averaging over the probabilities in X. And so those are the two marginals of my joint state. And with this kind of graphical language, I can write down a kind of abstract categorical form of Bayes' rule. Because these pictures don't really let us do division, I just do it in this kind of product form. It says that these two ways of factorizing a joint state are equal. So I've got this one where I've got this conditional, this likelihood here, and this prior, and then this is the other marginal, and then this is what's sometimes called the posterior. And interestingly, it's kind of a channel from, so this is the channel from X to Y. And now this other thing here, which I'm going to call the inversion, is now a channel from Y into X. And so it sort of goes the other direction. So we get a hint of this bidirectionality that Geoff was talking about. So of course, if we can do division, I can move this marginal probability onto the other side by dividing, and we get the standard form of Bayes' rule, which says that this posterior is given by this formula here. Now, a thing that has always frustrated me about the way that Bayes' rule is often presented is that this posterior is not really just a state, it's a channel. It's a state for every choice of Y. And not only is it a channel, it's a channel which is dependent on the choice of prior, pi here. And so I write this inversion channel for C as C dagger pi. The dagger is often used in category theory to represent this kind of transposition operation that allows us to go kind of backwards if we've got something that goes forwards. But this is a kind of transposition that goes backwards, but also depends on the prior that we chose originally. Now, this means it's something a bit lens-like. So now notice, as I say, these things point in opposite directions. The channel C goes from X into Y, and the inversion with respect to pi goes from Y into X. But if we let pi vary, then we obtain a parameterized notion of inversion. It's parameterized in the sense of this power construction that I mentioned before. And now it's parameterized by distributions over X. And so it's a map like this. It's from dx and y into dx. And so now we've got this thing which is a pair of a morphism that goes forwards, x into y, and another one which is parameterized and goes backwards. It's from dx and y into dx. And this is something that's like a lens. In fact, it is a kind of lens. And because it's got x's on both sides, and it's got y's here, both of them are y, it's called a simple lens, where the two objects of the pair are the same. This is what simple means. And because it's got this funny distributions thing being the parameterizing object, I call it a Bayesian lens. Whereas before we had just a set, this is a kind of special set. It's a space of distributions. So these pairs are things that I call Bayesian lenses. And in particular, I mean, we've seen before, Jeff was talking about this as a kind of prevalent pattern. It's interesting that this comes up in learners in the kind of machine learning sense. It also comes up in learners in the statistical sense. I think of these things as formalizing abstract statistical inference systems, or maybe a little bit more precisely, or maybe a little bit more intuitively rather, they kind of formalize the process of doing prediction. So this says, given a belief in X, I form a prediction about observations in Y. That's what this C is doing. And then this C dagger thing is saying, given my belief in X and the observation I actually got, what would have been a better belief to have started with? That's my posterior. So this is the thing that says, oh, I make a prediction, but then I can somehow improve it as well. Now, just as we saw that the derivatives compose according to this kind of lens composition rule, is also interestingly the case that this is true for Bayesian updates. And so I have this paper from 2020 called Bayesian updates compose optically, where I prove this, but here we can do it quite quickly using the graphical calculus of lenses and the graphical calculus of the Markov category. Now we can draw the kind of bidirectional lens thing as a funny kind of information flow diagram like this, where we've got something that goes forwards on the top and backwards on the bottom, and the kind of thing that goes forwards also comes into the backwards pass. And we can sort of compose them like this, just by sort of putting them next to each other. Now, if we follow through the information flow, and I'm not expecting everyone to do this just now, but I'm sure the slides will be available later, and you can sort of trace out the wires, we can see that if we do this, and we obey the law of copying, which says that if I have this C here and it's before a copier, it's the same as doing C after the copier twice on each side. That's what's happened. That's what's happening here. I'm going to sort of push this C forwards through this copier. Here, it's on the other side, notice, and I've got another C here. So if I do that, then I can sort of write down a composite forwards map, that's this thing, as well as a composite backwards map. And this is what the composition rule is. The forwards map is just composed like this, and the backwards map is composed in this funny sort of backwards way where I sort of reverse the order, and I have to sort of make my prediction be part of the prior for the kind of second level inversion map. This is exactly the same pattern that we saw that Jeff sketched out for learners. And so given this definition of composition of inversion maps, we might wonder, is this what Bayes' rule says? If I've got this kind of hierarchical channel as one kind of a way of predicting, and then one level of abstraction and then another level of abstraction, if I want to invert that sort of hierarchical predictive model, is it the same as inverting the two parts and composing them according to this rule? And that's what this formula is down here. It says, is the inversion of D after C with respect to pi the same as the inversion of C with respect to pi after the inversion of D with respect to C after pi? And the answer is possibly surprising. I mean, I was slightly surprised, but this is what we were saying earlier about the maths kind of making it be true when you've got the right structure. The answer is yes, that Bayes' rule does say that this is how Bayesian inversions compose. And the proof is really quite simple in the graphical calculus. So remember this picture I drew before of what it means to satisfy Bayes' rule. It was this thing where I had a channel at the top of this fork and then a way of kind of switching it around to the other. Well, if I just do that process twice, I've got this D dagger thing and this D here, and I can use Bayes' rule to switch it round to the D on the other side. And then I do the same thing for C, and I get exactly this expression. Look, this says D after C, that's this thing. And this thing says C dagger pi after D dagger C of pi, that's this thing. And so really, it is the case that Bayesian updates compose optically. This is to say that Bayesian inversions compose according to this lens rule. And interestingly, it seems to justify in a sort of abstract way some of the bidirectional hierarchical structure that we see in cortical circuits as a kind of as modeled by these papers that I was referring to at the beginning. It's interesting. I should also just point out, since Jeff mentioned it, there is this kind of functorial embedding of the Kleisli category that I started with, this kind of category of stochastic channels, into Bayesian lenses that just gives you this canonical choice of backwards map, which is the Bayesian inversion. Now, unlike in the machine learning case, where it's actually the desired thing to do to choose the actual derivative, in computational statistics, doing the exact Bayesian inversion is actually often quite difficult. And so often we want to do something else. We want to do something a bit more approximate because it's good enough and it's easier to compute. And really, that's what most real systems seem to do. But to kind of formalize how good it is to do inference or how well your approximation is performing, we need a kind of a bit more structure. And this is the thing that I call a statistical game. It's a game in the sense that when you play it well, you're doing inference properly. But the question, that clearly arises is what makes for a good approximation? Well, the answer I kind of alluded to in my earlier talk is that it depends on the context, which is to say that it depends on how the Bayesian lens interacts with the world. That means it depends on the prior we choose. Of course, if you have a prior that's well matched to the world, your approximation doesn't have to, may not have to be quite as, complicated because you're already doing well. But it also depends on the data we observe. So some approximation schemes make assumptions about the kind of data that they're going to receive and won't perform as well under other conditions. So the way we're going to proceed is to build another kind of category. So we have this category of channels, we have this category of Bayesian lenses, and now we're going to build a slightly more complicated category, which is this category of statistical games. And the way this is going to work is very simple. It's just to pair each lens. And now here, the backwards map doesn't have to be the exact inversion. It can be just something that computes it approximately. And we're going to pair that with a sort of contextual fitness function. So that says, given a context, how well does that lens do at approximate inference? Now, I want to make this a little bit more formal. I'm not going to go through all of the details because you get these quite complicated formulae here. But I want to draw this picture because it makes it hopefully quite clear that it is a context is everything that is required to make this open system, this lens which takes in inputs and produces outputs. I'm going to say that a context is everything required to make that lens close. And so we put something off at the beginning and something on the end. And now, as you remember, I drew this box earlier, which is like a diamond, and I said this is a closed system. Well, here we have a diamond. It has trivial inputs and it's got trivial outputs. I also allow there to be some kind of, environmental, contextual message passing. So it's not just the lens. There's possibly other stuff happening around it. I mean, that's just how the world is. And that's why we get this complicated kind of funny expression. It's to say that we have to account for this other stuff happening. But if we ignore this other stuff, then this pi, it really reduces to just being a prior. And this k, I call it k because of the k sound, it becomes something that's called a continuation. It says, given predictions that are made by the system, I go and do something out there and I come back to the system with some kind of input data. In the case of machine learning, that might be the data set. But in the case of kind of more biological systems, it could be how the environment responds to the way that the system behaves. Okay, so using this notion of context, I'm going to write down this definition of a category of statistical games. The objects, so the objects, as Jeff mentioned, of the category of lenses are pairs of sets. And the objects of my category of Bayesian lenses are again pairs of sets. And so again, the category of statistical game has the same objects being pairs of sets. So now the morphisms are, if I have this pair XY and I have another pair YB, a statistical game from XA to YB is a pair of a lens, which I write C and C prime, C being the forwards map, and C prime being the backwards map, from XA to YB. So that's the thing that does prediction and possibly approximate inference, as well as a loss function from the context of CC prime. So that's a prior, something like a prior on X, and a kind of a continuation from Y to B. And it says, given a context, how well does that lens do in the context? And I'm assuming that's going to be like a real number. How do these statistical games compose? Well, I've already sketched out how lenses compose. They compose according to that kind of that funny wiring diagram I drew. And then the loss functions compose by summing up what are called the local fitnesses. Now, what does this mean? Okay, well, if I have a context, if I've got like C prime into R, and then another thing, which is like D prime into R, then I've got, and I see I've got a context for this whole thing. Then I can make a context for CC prime by just including DD prime into the right-hand part of the context. And I could make a context for DD prime by including CC prime into the left-hand part of the context. So I get a context for each component of my composite lens. And so I get a real number for each component. And then I can just add those up, which gives me another real number. And so that's how I get a loss or a fitness for the composite system. And identities then are given by identity lenses. These things with kind of trivial forwards and backwards maps. And the loss function just returns 0. So if you add it to a number, it doesn't do anything. And this notion of statistical games turns out to capture quite a lot of statistical problems or inference problems. And really, they're kind of characterized or classified by the types. So a basic one is, what happens if we have kind of trivial domain types? They're just like these singleton sets. Well, now we've got kind of no backwards information because there's no updating to be done if you're just if you are just landing in this singleton. There's only one choice. So the only data is the forwards part, which is a distribution on X pi. This is, so as I say, I meant inversion part. Oh no, sorry, that was correct. Oops. I should say the prior part is trivial because, of course, there is no prior. There's nothing to, there is only like a trivial distribution on one. And so then we have, okay, so what's a loss function? Well, it's something that just takes in data or this continuation and then returns a real number. And maximum likelihood estimation says, okay, well, I should average the kind of probabilities given by pi according to the data I've received. And that will give me my loss. And a well-performing system is one that's going to give me a high average probability according to my data, because effectively it's modeling the data well. And so a good maximum likelihood estimator is one that maximizes this loss function. So that's nice because it just fits into this package. Now we can do Bayesian inference as well. Now we have a slightly more complicated system here. So we've got a kind of non-trivial domain, and we're going to keep it a simple lens, so it goes from X to Y. So we think of the forwards part as doing prediction, and the backwards part as doing approximate inference. And I say, given I write this complicated thing, it means, okay, this is data sampled from the context. So given data sampled from the context, I want to say, on average, how far away is my approximate inversion from the true posterior, which is given by this dagger map I mentioned before. And that's given by something like this, called like Leibler divergence between the two distributions averaged over the sampled data. But sometimes it's still hard to compute this divergence. We might not, for instance, know what this exact posterior is. And so a thing that people do, particularly in the context of predictive coding, is that they approximate it by something that they can compute, something like this thing here, which is called the free energy. And notice here that we no longer have this C dagger as a term. So we don't need access to the exact posterior, but we can prove that this loss function is strictly strictly bounds from above this loss function. So the idea is, or at least the hope is, that if you're, say, minimizing the loss here, you're at least going to be not doing quite as badly as you might have been here, because this one has to be above this one. And this is really at the heart of the free energy principle. It's saying, okay, well, let's minimize a loss function that we can compute. And hopefully that pushes us towards doing good Bayesian inference. A thing that we can also point out is that this also has this part which only sort of depends on the forwards channel. So it's also at the heart of, in machine learning, the notion of autoencoder. Because if you optimize this loss function, not only do you do inference well, but you also do prediction better as well. And so this got this quite nice kind of bi-directional optimization thing going on. And I've got this reference here. I spell out a load of examples in a bit more detail in this paper. Okay, so that's the statistical side of this kind of problem of predictive processing. But I'm interested in real biological systems and things that are implemented as kind of, say, models of differential equations, or things that go out and act in the world. They're kind of dynamical systems. They're not just these abstract kind of statistical things. There's no kind of realization of the system in these kind of abstract pictures. So we need a kind of thing that I call dynamical semantics, a way of turning these Bayesian lenses, or at least these stochastic channels, into dynamical systems that do inference, that actually compute the inversion. And so we need another kind of category, a category that has a similar kind of structure so that we can actually create a functor so that the types kind of match in some way and the composition matches in some way. But here now, the morphisms are going to be dynamical systems on appropriate interfaces. A way to define such dynamical systems is to use, again, another category of lenses, strangely enough. I'm going to call these lenses Markov lenses because they're going to be like Markov, sort of open Markov chains. They're going to be stochastic dynamical systems because I'm in this stochastic world. And I'm going to write this category as like M lens. Okay, so we've got this lens pattern already in our minds. And so how does it work? Okay, the objects, they're again going to be pairs of sets. But now the morphism is not going to be like a Bayesian lens, or it's not going to be like one of Jeff's lenses. It's going to be something slightly different. It's going to be a function. So if I've got xa to yb, the forwards part is going to be a function, just a deterministic function. There's no kind of prediction or stochasticity going on here. It just goes from x to y as usual. But in the backwards direction, it's going to take in an x, and it's going to take in a b, and it's now going to return a distribution on a. Okay, this is fine. Okay, it's a kind of lens. I can do this kind of lens composition, and I get a category. But what's it got to do with dynamical systems? Well, it just turns out that if we write down a lens S to OI, this turns out to be a discrete time stochastic dynamical system with outputs in O. So at each time step, it gives me an element of O. And at each time step, it takes an input in I and its old state and gives me a new state. So we can kind of iterate this process. And that's because I've got these S's on both sides of the backwards part. So like, let's write out the types of this thing. If I've got this Markov lens theta, it's got a forwards part, which I'm going to write theta O, which is going to give me the output. It's a morphism, a deterministic function from states to outputs. And it's got this stochastic update map. So it takes in a state, an input, and returns a new state stochastically. Now notice that if I chose a state, an input set which is trivial, so it's just like the singleton, so there are no inputs, there's just one input to choose, there's no choice, then this would just be the same as a kind of just a standard Markov chain. It takes a state and it gives me a distribution over states, and I could just iterate that. The only difference here is that this takes inputs, so it's kind of like an open Markov chain. Now, I'm not going to tell you, so this is funny because this is SS to OI, and I might want to compose another thing like S prime to O prime, or to like, or rather to say it's got outputs in I and it takes inputs in, I don't know, A. And I might think, okay, this should be able to compose, A to I to O, but it doesn't really, these things don't compose as morphisms. Now, we can form a category of these things. In fact, it's what's called an index category. So we have for each interface a category of dynamical systems on that interface. And the morphisms of that category are just morphisms of state spaces that somehow are compatible with the dynamics. And then we can use the kind of indexing to do composition of these things. But that's a kind of lot of structure that we don't really need. I'm going to use these things to make a new category, another category that will allow me to provide the kind of semantics I was looking for. And this category is going to be a category of things that I call hierarchical, bidirectional, stochastic dynamical systems. It's a bit of a mouthful, but really it's going to be just what we need to provide dynamical semantics for these Bayesian lenses. So again, the objects are going to be pairs of sets, XA, and so, XA and YB and things like that. And so the morphisms are going to be something kind of weird. They're going to be stochastic dynamical systems of the kind that I mentioned a moment ago. But now these stochastic dynamical systems are going to output a Bayesian lens. So this type O for XA to YB is actually going to be the Hom set Bayesian lens from XA to YB. And so at each point in the state space, I'm going to get a lens by this output map. And the inputs are going to be the things that the Bayesian lens needs to look at to be able to do prediction and inference. So that's a state, a distribution over X, and an observation of data in B. So that's like this prior and the thing that the world gives me back, or the continuation gives me back. Okay, so now if we write down what that means, it turns out that a morphism in this category higher from XA to YB is a combination of a choice of a state space, which again, I'm going to write S, and 3 functions. It's going to be lens-like because, of course, the outputs are going to be Bayesian lenses. And then it's going to have a kind of update part, which is going to be what does the dynamics, or what makes or what allows it to kind of iteratively improve its approximation. So what are these 3 things? The first one is a forwards output channel, which kind of mimics the forwards part of this Bayesian lens. But now it depends on a state. It's kind of parameterized by this state. So it takes a state and a belief, say, and it gives me a prediction. And of course, as my states change, my predictions might change. In the backwards direction, it's the same kind of story. It takes in a state and a prior and an observation, and it gives me an updated posterior. And again, as the states change, so might the posteriors. And of course, in the case of simple Bayesian inference, this A is also X, and this B is also Y. But now there's this other bit, which is the dynamics. And that says, okay, now I observe my prior again and my observation, but now I can change my state. So I can say I can improve my predictive model. Okay, so these things, this is a set of morphisms. And so we should ask, okay, so what is the composition? Well, it works a bit like this parameterized, this kind of category of parameterized morphisms that I mentioned before. It works by, say, taking if I've got XA to YB and YB to ZC, and I've got a state space S and a state space S prime, then the state space of the composite system is going to be S times S prime. So that's fine. That's how I mentioned this parameterization thing worked before. Okay, but then what do we do with these kind of outputs and inputs? Well, to compose the outputs, well, we've got Bayesian lenses, and we know how those compose. So the output of the composite system is going to be the composite lens that is obtained by outputting this lens and outputting this lens and composing them. And then, okay, so then given this composite dynamical system, I need a way to obtain the update inputs, the inputs to the update part of the 2 factors. How does that work? Well, it works in a similar kind of way as this context thing before. Remember, I drew this thing, and I said, okay, well, if I have C and D, I can sort of include these into the left and right parts of the context. Well, I can do a similar kind of thing for the inputs here. And if we have time or if we want to later, I could draw out how it works. But effectively what it does is it says, okay, well, to get the kind of forwards, okay, the forwards input for the S part is just the forwards input that was given. The forwards input for the S prime part is just obtained by pushing the S input through the output of the forwards part of the output. And I get an input in Y. And there's a similar thing that happens backwards. So I've got this input in C. That's all I need for this part. But I need an input for this S part. I just push that back through the inversion of the output of the S prime system. In words, it sounds complicated, but if I drew a picture, it would be straightforward. I mean, I've got this slide here. I'm not going to draw it right now, but I could show you how to do it if we want later. Okay, but this is kind of coming up to the end or the kind of the climax of the talk, as it were. So how do we put all these bits together to get a system that actually does approximate inference like a neural circuit might do? Well, it's going to be this thing that I call an approximate inference doctrine, which is really just a functor from my Markov category into these like hierarchical stochastic dynamical systems. So it's a functor that takes in a composite channel, something that we might think of as like a hierarchical generative model, and it returns dynamical systems or their composites that do this inversion thing, like those neural circuits that I was thinking about at the beginning. And really, these things behave nicely, or most nicely, if they factor through a category of statistical games. And in fact, it turns out that the kind of neural circuits that I was thinking about originally, these predictive coding circuits, really do factor like this. The first factor, it takes in a particular kind of, or like a subcategory of this Markov category, the stochastic channel, the model that we start with, and it returns a statistical game where the loss function is given by something that they call the Laplace approximation. It's a particular choice of loss function, which is an approximation to that free energy I showed. And then the second functor takes that statistical game and does stochastic gradient descent down the loss function. And that returns a bidirectional hierarchical dynamical system. And in fact, it preserves composites. And so this gives me this composite functor, which is the kind of thing that I was interested in up here. So this is really a way of taking these, as I say, these hierarchical generative models and returning dynamical systems, which maybe look a bit like neural circuits that actually do inference. And, my hope is that not only is this true for neural circuits, but I expect it's also true for other kinds of approximate inference systems, like Monte Carlo systems, or I don't know, maybe there are other kinds of dynamical systems, things that people call, I don't know, something like particle filters that also fit into this pattern. I'm in the middle of sort of finishing a paper where I spell all this all out. It's going to be the sequel to the one that I referred to earlier. Okay. Yeah, I think this is my final slide. So we really do have something like this picture I showed earlier, where we go from this kind of abstract picture of what is an inference problem, where in the forwards part, we have this thing that does prediction. And in the backwards part, we have this thing that does kind of inference or, improving the beliefs on which we based our prediction. And it turns it into a dynamical system, which, if you squint, kind of has a structure of these informal diagrams that people sometimes draw in papers. So it's quite nice because it's kind of like a tentative first step towards, it's like an ingredient, like Geoff was saying, it's kind of like the kind of basic thing that we need for a categorical account of cybernetic biological neural systems. And yet there are lots and lots of details missing, right? So, these dynamical systems, they kind of look a bit neural-like, but they're not very plausible. That's fine. I'm sure that there are ways to make the translation look more like neurons that we can do. And then we're also missing, I started earlier talking about active inference, and Geoff was talking about action as being the thing which is output here. But for me, the thing that's output here is really not actions, it's predictions. And so there's something else to be said for doing action. And I have some ideas about how that might go. Okay, And then there are other bits missing, like how does it mean to plan? How do we update our, how do we form our beliefs so that we can act according to the way the world is structured? And it's still, I mean, even with all of this structure, we're still quite far from cognition. So I introduced myself motivating things like, neural coding, or, the relationship between the world in my head and the world out there. And it's kind of still missing. But as we say, it's all kind of just small steps for now. But yes, that's the end. Thanks for listening. Any questions? I'd be delighted.
Thank you, Toby. So questions from the online community? We got questions here in the room. It is a long day, and long for you and long for our audience too. Michael?
I guess one question I have is, a lot of this stuff seems to rely on having exact representations, exact objects to act on. Is there any notion of representing uncertainty not representing uncertainty with category theory, but in category theory? Or is that a question?
Yes, I don't really have. No, it's a great question. I don't know if I need to have my slides showing anymore. I'd like to, I don't know. Maybe oh, whatever.
They are visible to us. We can't see them.
Okay, well, I mean, I don't have a slide on this, but I drew, let me see if I can make a new slide. Yeah, add page. I drew these pictures before, like A, B, C, like something like this. And then I was asking, okay, well, we might want to say that this thing commutes or not. And I think we can do is fill in this square with like a number, which is like, oh, it maybe commutes it up to like some probability, or we might be able to attach some numbers to these morphisms, which say how well we could choose them. So another thing we can do is say, parameterize this morphism by some noise. And then this, okay, then we've got something which is like an uncertain morphism. And then we can sort of do Bayesian inference up into this parameter object, or we could do sort of backprop up into this object. And that allows us to say, okay, well, I want to improve my, say, choice of morphism. But it's true that it's not really in the categorical language to say kind of purely that this commutes or not. You can sort of add this kind of thing in as extra structure using the notion of enriched categories. I think there was a paper a few years ago called something like, or on something called metagories. So the idea of these like metric approximate categories, where you have this kind of notion of approximate composition. It's it ends up being quite a sort of somehow quite a complicated structure, even though it's trying to get at something quite natural. And I think it's not something that people use an awful lot, but it's definitely something that comes up quite a lot in discussions with people about the applicability of applied category theory. So I think these two, I mean, as far as I know, I think these two things are the two main ways of thinking about it, having some kind of parameterization, which we could sort of use to represent our uncertainty or choice of morphisms. And then this other thing that allows us to say, like, how well do how equal are my diagrams? They might be equal almost. Maybe Jeff has got some, I don't know, some more thoughts on it.
I was just going to say saying something similar about enriched categories. Yeah, I mean, a category, that was Toby was saying as well. I mean, categories are sort of very set on what the arrows are, but when you have enriched categories, more general version, now your arrows can be different types of things in some sense. So that could allow for the possibility of probabilistic or uncertainty in those arrows. But I don't know much about sort of metagories or things like that, but that could be a possibility.
I think Jeff, metagories are categories enriched an appropriate kind of space where you can talk about distances and make these kind of things commute up to those distances.
Okay, so more questions from online. I don't think I see any in those of us who are still in the room here.
It doesn't appear to be any online questions, but if I may, I have one.
You're online, you count. Go ahead.
Okay. There are any attempts to build a model of metacognition using category theory? In the sense that because you were talking about Bayesian probabilistics, and now you add uncertainty, and it appears to me that it may have a possibility to build a type of model.
Oh yeah, I mean, it's certainly something I'd like to think about, and something I do occasionally think about. And I know other people in the kind of applied category theory world sometimes think about the same kind of thing. But I don't, as far as I know, nobody's actually written anything down on it yet. There are a lot. I mean, I'm not an expert on metacognition myself, but I think possibly some of this stuff about learning how to choose morphisms or learning how to sort of set up my generative model might be kind of a way forward along those lines.
Thanks.
Okay, well, maybe as a last couple of words, Michael, can you throw up that web page there? So those of you who are still with us, you've had quite a trajectory. So you kind of listened to me present some of the basic vocabulary, and maybe it's new, but you think like, okay, I think I can kind of follow that stuff. And then as the afternoon wears on and things get more technical and cutting edge, and you're hearing things that are appearing as archive preprints, 2021, 2022, 2020, or maybe a little more despairing of whether you're going to get to the end of your journey. And I think it's nice to have signposts like this article was helpful to me, or this was good about this review or this textbook that helped me in my progress to start wrestling or understanding some of these ideas. And I think those of you who are around, if you're interested in working on this, we can sort of build a little resource for ourselves. So part of the goal of the, I don't know how well it's showing to the online people, but there's a GitHub, Britt Anderson, which is my name. And then there's one that's pretty obviously says something like 22 Category Theory Workshop. That's where the presentations are. 2 of them are now there. Toby sent me a slides. I'll move those over. But also we have a thing called Bibliography where we can sort of build comments like this, like here's books and here's category theory for the sciences, and it can have a reference, and I can give you some of the thoughts that I had when I read it about what I felt was good or bad about it, or where it fit into my own learning. And if you read books or you read articles and you think this was useful to sort of not just have the scholar Google, headline and abstract, but actually one of us sort of talking about how it fit into our learning, I think that could be very constructive. So if you've ever used Git or GitHub, there's an issues button. You can basically click it and you can leave like a comment. So you can say like, you could create an issue and said, here's a reference, here's what I thought. And then I could go ahead and add that to the bibliography for everybody. Or if you know what you're doing, you can actually generate a pull request. You could clone the repository, add your own reference list in there to the bibliography file, and add whatever other ones you wanted, and we could rebuild it, and so it would be there. So if you have thoughts for how we might better create a resource for people who are interested in cognition and want to have a learning resource for category theory that would kind of help them chart their own course or progress, I'm happy to do some work to try to, support that infrastructure by adding things to the repository or updating it or compiling it or things. So I would encourage you to send those suggestions to me, or make issues or make pull requests, depending on your technical confidence. And otherwise, we have just a few minutes left. If anyone wants to make any general comments or questions, I'll wait and see if anybody chimes up. Anyone online? Okay, so I think hearing none, we still do have a few participants on there. So that's great. Okay, so that's it. I guess, yeah, I don't know. We can still end early, but I do want to end on a note of sort of my own positivity and try to hopefully promote others to sort of follow this path. I think there's a lot of value in this language in terms of its precision, in terms of helping you see the parallels across different structures, in terms of even sort of operationalizing your ideas, forcing you to be concrete. And I think it's possible to make that journey without having to go back to school and get a graduate degree in category theory. And so I hope that some of you will feel like you want to do some of that work with us, and you'll share your progress with me so I can learn some more. So thanks to all of you still here. Thanks to you, those online, and thanks to all of the presenters who spent their time with us. And thanks to all the technical people too, who hung in there and made it possible. So, all right. Thanks all.
Thanks, everybody.